Beneath the frozen shell of Saturn's moon Enceladus sits a global liquid water ocean. We know this because the crust fractures, venting massive plumes of subsurface water directly into the vacuum of space. The chemical composition of that water is no longer a mystery. During its 13-year mission, the Cassini spacecraft flew directly through these plumes, using an onboard mass spectrometer to sample the erupting ice grains and gases. These samples were collected nearly 1 billion miles from Earth, mapping the chemistry of an alien ocean from orbit. This chart shows the concentration of phosphates found in the Enceladus plumes compared to our own planet. The data reveals that phosphate levels in the Moon's subsurface ocean are at least 100 times higher than those found in Earth's oceans. Phosphates are a strict requirement for standard biology. They form the structural backbone of DNA and RNA, and they create the cellular molecules required to carry energy. This abundance is driven by enhanced phosphate mineral solubility, a geochemical mechanism that allows these critical minerals to dissolve easily into the liquid water of icy ocean worlds, making them readily available for potential biology. But confirming a perfect geochemical environment only solves the baseline habitability equation. Finding the chemical ingredients for life does not prove life actually exists there. For decades, the search for extraterrestrial life relied on a highly specific methodology. Early in-situations, like the Viking Mars landers, were designed to hunt for the exact metabolic indicators and organic compounds produced by Terran, or Earth-based life. That approach is now recognized as severely limited. The 2018 National Academy's Astrobiology strategy outlined that searching for known, specific molecular structures often fails because those structures do not survive in harsh planetary environments. The limiting factor is taphonomic attrition. Over geological timescales, particularly in low-energy environments, physical and chemical processes relentlessly degrade or destroy organic matter. Abiotic geological processes erase biological signals, like molecular racemization. Biological systems produce an enantiomeric excess of right or left-handed molecules. Over time, abiotic chemistry forces them to interconvert into an even mixture. In low-energy environments, abiotic destruction outpaces biological production, swallowing life's signature. Life detection requires moving beyond the search for a single, easily degraded molecule. It requires calculating the statistical improbability of a complex signal, standing out against an overwhelming abiotic haystack. Hunting for terrestrial genetic polymers, like DNA or RNA, is largely unviable for ancient samples. These molecules are highly susceptible to chemical and enzymatic degradation. The alternative is the agnostic biosignature. Instead of looking for specific Terran biochemistry, researchers look for functional complexity, molecular assemblages so intricate that their formation without biological instruction is highly improbable. A primary target is the informational heteropolymer. These are long molecular chains containing multiple types of structural subunits arranged in non-uniform, aperiodic sequences. To read these unknown polymers in situ, instruments use advanced mass spectrometry. The polymer chain undergoes spontaneous cleavage inside the spectrometer, fragmenting on the fly so its internal composition can be measured. Even if the exact chemical makeup is unknown, analysts can look at the spacing of electrical charges along the polymer. A discernible phase mismatch or a complex, regular variation in charge spacing indicates a high level of contained information. Identifying this kind of abstract thermodynamic improbability proves that an organized system assembled the molecules.
That is a far more robust metric for life than searching for familiar, fragile DNA. This concept of abiotic interference scales up dramatically when we shift from microscopic rock samples to remote, global-scale observation of exoplanet atmospheres using next-generation observatories. For a long time, the astronomical community operated on a straightforward assumption. The simultaneous presence of atmospheric oxygen and methane in strong thermodynamic disequilibrium was a definitive marker of an active biosphere. But planetary physics can spontaneously generate atmospheres that perfectly mimic these biological outputs. A high-risk scenario occurs with terrestrial planets orbiting late-type M-dwarf stars. These stars emit a high ratio of far and near ultraviolet radiation. When this intense energy strikes the exoplanet, it drives a runaway greenhouse effect, rapidly heating the surface. The extreme surface temperatures boil off existing oceans, forcing immense volumes of water vapor high up into the planet's stratosphere. Once in the upper atmosphere, the stellar radiation drives photolysis, physically splitting the water molecules apart. The lighter hydrogen atoms readily escape the planet's gravity and bleed into space. The heavier oxygen atoms are left behind. Over time, they accumulate, forming a dense, abiotic oxygen atmosphere that can be hundreds of bars thick. Similar massive abiotic oxygen levels can be generated through the photolysis of carbon dioxide or by the splitting of liquid water via a titanium dioxide surface catalyst. An exoplanet can display vast quantities of oxygen while remaining sterile. The simple presence of the gas is no longer an isolated proof of life. Because geology and stellar physics can mimic biology, biosignatures cannot be treated as binary detections. They must be evaluated as conditional probabilities. Frameworks like the ladder of life detection deploy Bayesian probability to quantify confidence levels, mapping the likelihood of biological origins against known abiotic alternatives. This ROC curve plots true positive rates against false positives. An Earth-like biological oxygen signature produces a clear true positive curve, but abiotic oxygen from a runaway greenhouse effect plots a false positive curve directly over it. Without additional data, a simple measurement of oxygen sits right in this overlap. It is statistically indistinguishable from the planetary baseline. To shift the probability out of the noise, researchers must look past the target gas and measure the broader planetary context. They look for planetary tells, environmental anomalies revealing a gas was generated by planets, not a biosphere. One primary discriminant is searching for collision-induced absorption of O4 molecular pairs in the atmospheric spectrum. O2 molecules only collide frequently enough to form O4 in hyperdense atmospheres. If O4 is present, it indicates massive abiotic water loss, immediately flagging the system as a false positive. A second discriminant is the presence of carbon monoxide in the atmosphere. Detecting carbon monoxide alongside oxygen proves the oxygen was generated by high-energy photolysis of carbon dioxide rather than by biological photosynthesis. By identifying and mathematically eliminating these specific tells from the dataset, the false positive rate on the probability matrix is forced down to 0. This multivariable systems analysis is the only method to separate true biological disequilibrium from geological chemistry. The ultimate signature of life is not a single molecule. It is functional information and thermodynamic disequilibrium, measured rigorously against an immense abiotic universe.